So we have done enough thin wall. Okay, thin wall is, I think it's a very interesting topic. The next topic that we're going to deal with, okay, before I go on, how many of you design your own deck and build your own deck? No, some of you do. I will encourage you to do it, okay? And with this calculation that I'm going to show you, your deck will never collapse. Okay, your deck will never collapse. Okay, with this calculation. So let's look at. You have all this in your in Avenue to Learn. Okay, I'm going to show you what are we going to deal with. I'm going to show you the problem first. I'm going to motivate you first. Okay, right. So now, so what are we looking at first? Okay, so this is our XY section. Then this view that you see, okay, so this is your YZ. So this is your cross-sectional area. Okay, right. So what do I mean by building a deck? Okay, question for you: when you build a deck, what is the spacing of those two nails? You get what I mean? You have now building a deck is not just I have a deck, I can barbecue now. Right? You want a deck that you stand, you feel what? Safe. Yes or no? You want a deck that when you lean, you know you're going to be fine. Okay? And it's not the landscaper's job or the builder's job to calculate all this. It's your job and it's my job, and I earn quite a bit of money out of calculating the spacing for some landscapers, which I can't mention names. Okay? So you can also now, it all depends on how much load you're going to carry. Did I tell you the story about me building Lego? Yes or no? No, some of you remember, some of you don't. When you build Lego in house, building a house, what do you build first? When I was young, I built the foundation first, then I built the roof. I realized that the roof have a piece that I have missing, or they don't make that shape. So what I do is I build the roof first, then build the what? Foundation. This is what civil engineering, this is how civil engineers build their structure. They design the roof, see how much load they carry, then they design the structure. Moral of the story is never stop playing. Okay, never stop playing. If I'm not playing Lego up to today, I'll be a boring bastard, I'll tell you that. Yes? Okay, never stop playing. Right. Likewise for this, okay? We know the load that we're going to carry. Okay, the trick is, what is the spacing of the screws? How much spacing you have to go? If you're not sure, what will you do? Every fist palm distance, I put one screw. Right? How many nails are you going to use? Is it going to be a big deck? No. Okay. There's a reason for how much screws to put in based on how much force is required to extract your nail or your screws. Okay. So there are reasons for design. Okay. So why is this different? Okay. Why is this different from what I thought before? If you look at the cross-sectional view, what do you see now that you did not see before? Anyone? Or online also. What do you see now? Okay. What do you see in the cross-section now that you did not see before? Anyone? Yes. Yeah. So the bolts, okay? I know. You say, why are you so excited when I say bolts, right? I get excited. Why? Where is this structure going to fail? Anyone? Yes. No. Where is it going to fail is here, okay? It's at the where? It's at the joints. Agree? Where it's going to fail, it's going to fail at the joints. Okay? So we are this get very exciting. Okay? We are going to do failure analysis. And the textbook got it wrong. I'll tell you what the textbook got it. The textbook got it wrong because they do this first and do thin wall analysis. Wrong. You have to teach thin wall analysis first, then you can do failure like this. Okay? So now, where it will fail, okay, there are two regions where it will fail. It will fail due to the shear at the centroid, okay, thin wall. It will also fail at the joints, okay. So how to remember this? Simple, okay. In school, I was not the biggest kid. I was a bit smaller, and I was been bullied because I cannot speak Mandarin very well. Okay, kids twice my size always want to beat me up. And I always tell them this: when you beat me up, make sure I don't stand up again. Yeah, there are incidents I can't stand up again. Okay. But the thing is this: I did not know this. I did not know where to attack them. Now I know. By teaching, I don't know any martial. I did 2.5 years military service in Singapore. Okay. I know where to attack them now. Where are you going to attack them? Anyone? We're going to attack them at the joints. Okay? Joints as in the elbow, the knees, and the ankle. Hit them there and they cannot stand. Okay? This is not a taekwondo class or what. This is structure analysis. Same thing. Okay? Someone 3 times your size, go for the where? Go for the joint. The problem is this. Don't miss. If you miss, you're done. He will go for your joint. Okay, enough humor. Okay, let's do some writing. Okay, so yeah, hope this will we will come to this problem. Okay, so this topic now. Any question? No question formula. So this topic now is known as longitudinal shear. On beam section. Okay. So the objective of this topic is to analyze the strength of joints in shear loading conditions. Okay, so where oh, I do apologize. I'm going to move this away. I'm going to use this diagram. Okay, I'm going to use this diagram. And as you can see, like what I mentioned earlier, right? So this is our cross-section view. All right. If failure is going to occur, if anything is going to occur, where failure will occur here at the joints. Okay. So failure will occur at the joint. Okay. So we are going to calculate. Okay, we are going to calculate the shearing stress acting on the joint. Now, there are two words that I like to mention. We usually call these members. Okay, so all these are our members. So when I address the word members, all these are known as members. Okay? The purpose of the member is to distribute the shear stress. The member is to distribute the shear stresses, number one thing. The next thing is the joint is to transmit the shear stress or shear stresses from one member to the other. Okay, you have to get the terms right. What is the objective of the member? The member is to distribute. Okay, so in between two members, you have a joint. The joint is to transmit the what? The load. Okay, to transfer the load from one member to the other member. Okay. Now, don't laugh at this. Okay, I'm going to show you something really, really funny. Okay. Oh, you guys are still copying? Okay. I'm going to show you something really, really funny. Okay. You only need two formulas for this. What is the formula? Shear flow is equal to VQ, or this is what we call small q, is equal to VQ over I. And if we look at the units, this is in Newton meter cube per meter 4. Okay. So when you cancel this, okay. And Q is also equal to the force that the joints would resist divided by the spacing of the fastener. Okay, or the force that the fastener, okay. So the units is also Newton per meter. Okay. So this formula looks really, really familiar, isn't it? Right. Seen this before, man. Right? I told you, right? This topic only two major formulas. The rest is analysis. Okay. And then we also apply the same thing, that the shear stress is equal to VQ over IT. The difficult part of this, okay, of this topic is require more failure analysis. Okay, you require more failure analysis. Okay, that is the only complexity of this topic. Okay, but I think the most difficult part is over already. It's the thin wall analysis. Okay, I can throw box beam, white French, thick wall, thin, non-thick thin wall, anything at you, you should be able to solve. Okay, now the thing is this: failure analysis. Okay, now let's get into this. Let's look at that's all the theory. Okay, that's all. Okay, next is the failure analysis. So I'm going to take this diagram. Okay, we're going to look at this diagram. Okay, so we have a structure. Then let's read the problem first. Okay, a double wedge girdle is constructed from 2 plywood sheets that are secured to wood members as is